Hey guys, so today we're going to be looking at the properties of ionic and molecular solutions. In the last video, I introduced you to the idea of a solution, and we defined a solution as a homogeneous mixture. In this case, we're going to be looking at two different types: the solutions created from dissolving ionic compounds into water, and the molecular solutions created by dissolving molecular compounds into water. Many of us have dissolved salt into water. For instance, when we're cooking pasta, we add salt into the water to add flavor and also raise the boiling point of the water that's in. And I'm sure many of us have dissolved sugar into water, specifically the morning coffee, which for many of us has more sugar in it than it does coffee. But nonetheless, we're looking in this case at either ionic or a molecular solution. We can see salt dissolving in water because we can see the solid going in and then somehow disappearing. And we can see the sugar going in and then as we stir it somehow disappearing. But what's actually going on? Well, these particle diagrams are really going to be able to show us what's happening at that microscopic level. Looking at an ionic solution first, in this case potassium chloride, KCl. Now, potassium chloride in the solid is in a crystal lattice. Now, the crystal lattice is completely dictated by Coulomb's law. Remember from Unit 0, Coulomb's law is the force of attraction is equal to the charge over the distance between the nuclei. In this case, the charge is going to be +1 for the potassium and -1 for the chloride ion. And then the distance between the nuclei is going to be determined by their individual atomic radii. This forms in the solid a crystal lattice structure. When a crystal lattice structured ionic compound goes into water, what's going to happen is the water molecules, knowing that oxygen is slightly negatively charged and that hydrogen is slightly positively charged because water is a polar molecule, the oxygen is going to be attracted to the positively charged potassium ion. That's going to pull it slightly away. The partially positively charged hydrogen ions hydrogen atoms are going to be attracted to the chloride ion, and they're going to slightly pull it away. Now, if this force of attraction between the water molecules on the ions is greater than the force of attraction by the ions into each other, then the reaction is going to continue and we are going to dissolve. So not only dissolve, but dissociate. And dissociation is critical. In the next video, we're going to look a lot more at the rules of solubility. Because what solubility means in an ionic solution is that not only do the ions dissolve, but the ions themselves actually separate into cation and anions individually. Even though we have ions present in an ionic solution, it's actually going to be an overall neutral solution. So the reason for this is because every KCl that goes in, you create one K plus and one Cl minus. So the ratio stays the same. So the solution as a whole is neutral as it pertains to its charge, even though we have the ions in solution. So it's not just one water molecule that's pulling a potassium or one molecule that's pulling a chloride ion apart. In fact, at the molecular level, you have many water molecules that will be working essentially together to pull apart the potassium or chloride ions. This process we are going to call hydration. Hydration is the process by which water is going to surround particles in a solution. So that's what happens when ionic compounds dissolve in water. They dissociate. When molecular compounds dissolve in water, it's a little different. When molecular compounds like sugar here dissolve in water, what happens is the molecules will separate from each other in hydration, but they will not break apart within each other. So in other words, a sugar molecule, even when dissolved, stays a sugar molecule. It doesn't break apart within itself. This is important because what it means is that it retains the properties of the molecule. When ionic compounds break apart, their physical and chemical properties both change. But when a molecular compound dissolves in water, even though the physical properties might change, the chemical properties do not. It's a very important idea. So when we're looking at these mixtures of molecular compounds, how does it happen? Well, water is polar. This means that the hydrogen side of water is partially positive and the oxygen side of water is partially negative. Molecular compounds such as sugar are also polar. Now, not all molecular compounds are polar, which is why not all things dissolve in water, but sugar is polar and therefore will dissolve in water because of the fact that the oxygen, the partially negative side of water, is going to be attracted to any partially positive charges in the sugar molecule. Additionally, the partially positive side of water, the hydrogen, is going to be attracted to any partially negative charges that happen to exist in the molecule. The more polar the molecule, the more readily it will dissolve in water. This is critical. We can actually predict with this idea how readily soluble any molecular compound is in water using this idea. We're going to talk a lot more about the forces involved and the relative polarities of molecules in Unit 5 this year when we start talking about interparticle forces and molecular geometries, but it's good to understand the idea of polarity and nonpolarity now so that we can have these discussions. One thing to be aware of is that solutions will change the overall properties that exist in the water itself. So when we go from just pure water to a solution, the difference between an ionic solution and molecular solution can become apparent. First of all, ionic solutions readily conduct electricity. This is because the actual ions in the solution are electrolytic. What that means is that ions can actually pass electrons across the solution. So think of it like empty benches. So if you have a bench from here to here to here, and you're playing a game like the floor is lava, you can jump from bench to bench to bench, no problem, because that's a great place to go. Molecular compounds, however, don't have empty spaces for electrons. Therefore, they do not conduct electricity. So if I have a saltwater solution, it will readily conduct electricity, but if I have a sugar water solution, it won't. In addition, we have things called colligative properties. Colligative properties are properties that change relative to the amount of stuff in a solution. What I mean by this is that if I have more stuff in a solution, the properties of that solution will be different than if I have less stuff in that solution. Good example of a colligative property is going to be both boiling point and melting or freezing point. Boiling point with more stuff goes up. So if I have water and I add more stuff to that water, either molecular or ionic stuff, the boiling point's going to go up. If I had stuff to water, the melting point or freezing point will actually go down. So what ends up happening is as a result of adding stuff to water, we can change the melting point or the boiling point of the water. This is a great example where we add salt to water when it's boiling to increase the boiling point of the water when we're, say, making pasta. Or when we try to melt ice in the wintertime on the roads, we simply add salt, and that helps lower the melting point of the water, which allows us to essentially drive on wet roads as opposed to frozen roads. Let's go ahead and do a practice problem. In this problem, what I want to do is assume that this ionic compound is fully soluble. In the next video, we're actually going to talk about how to predict solubilities of certain compounds or relative insolubilities of others. But let's assume for a moment that this compound is fully soluble. If this compound is fully soluble in water, I want you to draw the particle diagram before and after dissolving it in water. So go ahead and take a few seconds, draw a particle diagram of a before and after situation, where before it's dissolved in water and after it's dissolved in water are in two separate boxes. Additionally, I want you to include at least 10 water molecules in your drawing. You can't just draw a few water molecules and truly represent what's going on. So go ahead and take a few seconds, draw this. When you get an answer, or if you get stuck, go ahead and unpause the video. We'll work through it together. All right, now I've had a couple of seconds to work on it. Let's go ahead and go through it together. First things first, we need to draw a box with the solid sodium chloride over here on the left. When we do this, remember it's in its crystal lattice structure. Now, one thing I did not mention, but is critical in drawing particle diagrams, is that we represent relative size of the particles as well. The chloride ion is substantially larger than the sodium ion, so we need to draw it as such. We're going to learn in further particle diagram drawing videos how to make sure we represent relative size properly, But in this case, you need to make sure you do it. So if you didn't draw it with the correct size ratios, you need to go back and do it. It doesn't have to be perfect, but the chloride definitely needs to be bigger than the sodium ions. It also is going to be regularly interspersed. Chloride and sodium are going to be next to each other, but each sodium ion is going to be surrounded in this two-dimensional drawing by 4 chloride ions. All right? You don't actually need to know about what the actual structure or shape of the lattice is. Relatively speaking, there are a lot of complexities there. You just need to be able to understand that the positive and the negative are going to be next to each other in this case. Once we dissolve in water, what's going to happen is water molecules are going to surround each chloride and sodium ion while separating them. The oxygen of the water is going to be attracted to the chloride ion, so you needed to have drawn oxygen atoms next to or relatively close to the chloride ions. And we need to make sure that every sodium ion is surrounded by water molecules, but the hydrogen sides of the water molecules. So double check your drawing. Generally speaking, we're going to be looking for 3 things. 1 is particle size. 2 is, relatively speaking, is it homogeneous? So did you draw them clumped together or did you draw them fully separated apart? And 3, did you draw it with the right orientation of water molecules to the ions? This is how you will determine whether you did it properly or not. So take a look at my answer here, see if you did it right. If not, go ahead and figure out why that might have been the case that you got it wrong. So that wraps up today's video. Let's do a quick recap. Today we learned what happens when stuff dissolves. We focused on ionic and molecular compounds when they dissolve in water. We talked about the different properties of ionic and molecular substances in solutions. And one thing to be aware of is the fact that you'll oftentimes be given a property. So here's an unknown solution. What's this property? You will then have to predict whether it's ionic or molecular given the properties. The most common property given, conductivity. So make sure you're aware of the fact that ionic solutions are conductive while molecular solutions are not. The next thing to be aware of is the fact that you'll need to be able to draw these particle diagrams. So we represented particle diagrams throughout the entire video. Make sure you know how to draw those. You're going to be asked to do that repeatedly throughout this unit and over the course of the year. I'd like to thank Dylan Mahoney for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.